Alright, this is a review of a unit on circles. We're dealing with everything from basic circle terminology, radius, diameter, chord, secant, tangent, things like that. Also, we're dealing with the relationships between angles and arcs. And also we're dealing with the relationship between the segments inside of a circle. So that's all going to be covered by this review. But first let's delve into some basic circle vocabulary. What is the center of the circle? Well, that's point G. Name the radius of the circle. Well, it should say a radius because there are several radii. For example, GA would be a radius. Okay, and we should put the segment symbol over it because it's a segment. But we could have said segment GF or GC. Alright, these are all radii from the center to the edge. Name a chord of the circle that is not a diameter. Alright, the one that jumps out at me, well, two are jumping out at me right now. You would probably say segment AC first, because that's the one that doesn't have a secant line going through it. But technically I could say segment AB as well. As long as I put the segment symbol over it, it means the segment from A to B, not the line that happens to go through it. Okay, but the most common answer I'm sure will be segment AC. Name a secant of the circle. Well, a secant is a line that passes through the interior of a circle. So a secant line would be, for example, line AB. And notice I'll use the line symbol over the top of it. Okay, but technically I could talk about line AC as well. Even though it's not drawn in, it still exists. So I could have said line AC or line FA or any number of lines. But line AB is the most obvious. Name a tangent of the circle and identify its point of tangency. Well, the obvious one here is line ED is a tangent line with point of tangency E. Okay, now what kind of angle is angle APB? First of all, I think that's it for that picture up there. So now we're starting in on this picture down below. So with that in mind, angle APB, we're talking about this angle right here. APB. Well, this is an acute angle, and its measure is 72 degrees. Oh, you know, it's acute. Maybe they mean that it's a central angle. It's an acute central angle because its vertex is at the center. Maybe that's what they mean. Either way, its measure is 72 degrees because when you have an angle at the center, the measure of the arc and the angle are the same. Now, what kind of angle is angle CED? Alright, let's see. Let's do that one in purple. CED. Well, ladies and gentlemen, yeah, I think definitely they wanted us to say that it was a central angle before, because now I can see where they're going with this whole plan. That was a central angle. This is not a central angle. This is an inscribed angle. and its measure is going to be 24 degrees. How did I know that? Well, when you have an inscribed angle and its intercepted arc, the angle is half the arc. So arc CD is 48 degrees, so angle CED is 24 degrees. Now, what kind of arc is arc FBC? Okay, arc FBC, we're talking about this arc right here. Okay, pretend that it went smoothly right here. You see how this is going from one side of a diameter to another. That makes this a semicircle. Whoa, I messed that up. Semicircle. What is its measure? 180 degrees. What kind of arc is arc BC? Okay, the options are major, minor, and semicircle. So if we're going to talk about arc BC, between those options, this is a minor arc. Okay, but I know that the total here, because of the semicircle that we just spoke of, alright, so here is a diameter. So that means the total right here is 180 degrees. So I can just subtract 180 minus the 72 and the 24. Okay, so that is 84 degrees. Alright, what kind of arc is arc BFC? Alright, BFC goes all the way around like this. Alright, that is definitely a major arc. What is its measure? Well, this gray arc encompasses the entire circle except for 84 degrees. So what I can do is I can do 360 minus the 84 degrees, and it'll find out how big the gray area is. 276 degrees. Okay, find the measure of angle LMN. Let me be clear. Angle LMN is this angle right here. LMN. Let's call it, I'm going to call it theta, just for ease. So we're supposed to find the measure of that angle. Now, so this is what we are dealing with. This is the situation where we have these lines intersecting. So we have this angle and the two intercepted arcs. Okay, I have an arc here and I have an arc here. Okay, so the relationship is the following. That's too big. It goes like this. Angle is equal to arc plus arc divided by 2. Basically, the angle is the average of the two arcs. So the angle is the thing that we're trying to find, so that's perfect. So the angle will equal 174, whoops. Alright, 174 plus 42 divided by 2. $108. That's the answer to number 10. Alright, here's number 12. I think there is no number 11. If I'm wrong, I'll fix it later. Find the measure of angle RST. Angle RST is this angle up here. Okay, it's the only angle up there, so I'm just going to call it angle S. How about that? So remember, the way the formula is set up in a situation like this, when you were outside of the circle, the angle, alright, let me just write it in words. The angle is equal to the big arc minus the small arc divided by 2. Alright, so angle S, or I should say the measure of angle S, will equal the big arc, which is 77, minus the small arc divided by 2. So the measure of angle S is 21 degrees. So that's the answer to number 12. Alright, for number 13, we're supposed to find the measure of angle XYZ. Okay, so XYZ is this angle right here, XYZ. Okay, so it's this angle. Well, this is an inscribed angle. So we've learned that if I'm dealing with the intercepted arc, such as this one, the angle is going to be half the intercepted arc. So if the arc is 102, then the angle will be 51. Simply divide by 2. Alright, and that's the answer to number 13. Number 14, find the measure of the major arc in this circle. Remember, a major arc is greater than 180 degrees. So we must be talking about the arc that I'm about to show here in green, the long way around. Okay, so if the minor arc is 102, we will just subtract from 360. So we're just talking about doing 360 minus 102. In other words, 258 degrees. Alright, that's the answer to number 14. Alright, quick side lesson here. These three concepts are closely related. Alright, hold this picture in your mind and focus your eye on this chord, the green chord. Now, given any two of these three qualities, the third one is automatically true. So in other words, if this green chord is the diameter, and it is perpendicular. Let me check these off. Say if I told you that this green chord is a perpendicular diameter, we could conclude that it is also a bisector. Now the way I would give you diameter is I would give you a dot here in the middle showing that it's passing through the center. The way I would give you perpendicular is I would put a little box here to show that it's 90 degrees. So if you saw these two things happening, you could conclude that it's also a bisector. So if I told you that this length was 5 and I asked you what this one was, with confidence you could say this was also 5 because of this analysis. Similarly, if I told you that this green chord was a perpendicular bisector, alright, if I give you these two, alright, I would give you, again, perpendicular by putting a little 90-degree box right here. I could give you bisector either by marking these the same or putting equal numbers here and here. But by giving you these two things, you could conclude that this chord is also the diameter of the circle. So if it's a perpendicular bisector, it has to be the diameter as well, even though I didn't give you the dot this time. And one more, if I told you that this green chord is a diameter, that is a bisector, okay, and in a picture it might look like this. Here I'm giving you that's a diameter, and here I'm showing you it's a bisector. Then you could conclude that this is also perpendicular, even though I didn't give you the little box. So anything that you wanted to do with a right triangle, you could go ahead and do that. So that's what's going on here. Notice this dot that we have in the center. So I'm giving you diameter, or whoever created this worksheet is giving you the that this is a diameter. And of course you see the 90-degree box right here, so they are giving you perpendicular. So what's the third thing that we can also conclude if these two are true? If I'm giving you diameter and perpendicular, it must also be a bisector. So that means the left side and the right side must be equal, congruent. So if AB is 4 millimeters, that means BC must also be 4 millimeters. Alright, there's another theorem that says if you have a chord that is the same distance away from the center as another chord, it must be congruent. So you see these markings right here. Alright, that means that these two chords are equally distant or equidistant from the center. And since these two chords are equidistant from the center, they must be congruent. So here, for number 16, we are being asked what is the length of DF. Well, the length of DF will be the same thing as the length of AC. And the length of AC is 4 millimeters on the left, and therefore 4 millimeters on the right. So guess what? That's a total of 8 millimeters. So that's going to be the length of DF. What's the measure of arc DF? Okay, arc DF, so now we're talking about this right here. Well, off to the side we're given that the measure of arc AC is 94 degrees. And we know that if the chords are congruent, then the arcs will be congruent. So see these two green chords and these two fuchsia arcs. Since the chords are congruent, the arcs are congruent. So since arc AC is 94 degrees, then arc DF will also be 94 degrees. Number 18. If line LK is tangent to circle J, what is the measure of angle JKL? JKL. It's 90 degrees. We have a theorem that the radius of a circle is always perpendicular to the tangent at the point of tangency. So if this is a tangent, then this is a right angle. So 90 degrees. And that's the answer, number 18. Alright, number 19. We are given these two arcs right here. We're supposed to find the measure of arc MN. So this is our target right here. That's our target. But we know that these two are congruent because of the way they're marked. So let's start with our 360 degrees. If I start with 360 and I subtract the two angles, the two arcs that were given. So if I subtract 85 degrees and I subtract 65 degrees, let's see what's left. That is 210 degrees. Alright, so there's 210 degrees left in the circle, but since we know that these two arcs are congruent, then this 210 degrees will have to be shared equally between the two arcs. In other words, divide this by 2. So that's why the two arcs will be 105 degrees each. Okay, so that's why the answer to number 19 is 105 degrees. Alright, now that says part A. Does that mean there's a part B, or are they just mocking us? I think we were mocked. Let's move on. Alright, look at number 20. Find the indicated measure for circle P. So let's see. Arc BC is 50 degrees. So let's get that registered. So this is 50 degrees right here. AB, arc AB and arc ED are congruent. Okay, so this arc and this arc are congruent. So the measure of arc AE is what? So we're looking for this. Okay, so the measure of arc AE is our target. Okay, now remember the three words: diameter, perpendicular, and bisector. If we're given any two, then the third must be true. Well, see this dot in the middle? We're given that this is a diameter. See this right angle? So we're given that it's perpendicular. If we're given a diameter that is perpendicular, what can we conclude? It must be the bisector. So that means these two sides have to be congruent. Alright, which means the arcs have to be congruent. So if this is 50 degrees over BC, then arc AB is also 50 degrees. Now, we were told right in the given that arc AB and arc ED are congruent. See, that's why we marked them the same. So that means ED is also 50 degrees. Okay, and furthermore, because this is a semicircle, alright, look at this green. This is a diameter. So that means everything here on the left is a semicircle. Okay? And so how many degrees is that? 180, that's right. So we're given all of the semicircle except for this. So in other words, if we start from the total of 180 and subtract these two 50s, well, that's 180 minus 100. So that leaves 80. And that is what we're looking for. So the measure of arc AE is 80 degrees. And that's the answer to number 20. Alright, looking at number 21. When you have the segments meeting inside the circle like this, let's see, let me find the situation. The relationship is part times part equals part times part. For example, R times M equals D times K. So that is what we are dealing with. So in this case, the relationship gives us that x times 15 equals 18 times 10. X times 15 is also known as 15x. 18 times 10 is 180. So if I want to solve this for x, I will simply divide both sides by 15. Let's see, 180 divided by 15, that's 12. X is 12. So that's number 21. Similarly, number 22. part times part equals part times part. Okay, so I'm pretty sure that this is the 6, and this piece right here is the x. So part times part, 6 times x is 6x. So 6x equals, and then we have 9 times 4, which is 36. To find x, we just divide by 6 on both sides. So x is equal to 6. And that's how you do number 22. Alright, when the angle comes outside of the circle, the relationship between the segments looks like this. Part times whole equals part times whole. Now when I say part, it has to be the outer part outside the circle. So part times whole is d times k. And that will equal the outer part times the whole, r times m. Also be prepared to recognize it in this form. When you're not given the whole specifically, but rather these two parts, part times whole, that's the outer part d, and the whole is d plus k. So d times d plus k. And then part times whole in the lower secant segment is part times whole r times r plus m. Be ready for that. So looking at number 23, part times whole equals part times whole. Again, it has to be the outer part when I say part. So it's going to be 4 times x plus 4. Alright, the outer part times the whole thing. And that's going to equal 5 times 9. Again, the outer part times the whole thing. And so the rest is easy. So a little distributive property. So that'll be 4x plus 16 is equal to 45. Subtract 16 from both sides. So I have 4x equals 29. And then we have to divide both sides by 4. So x equals 7.25. So that is the answer to number 23. Now, number 24 looks a little bit strange, but it's still the same thing. Part times whole equals part times whole. The bottom part should be perfectly normal seeming. Part times whole, you have to start with that 6 as the part, and then the whole is 10 because 6 plus 4. Now, the other segment here, clearly x is the outer part, so I'm going to start with that. But x is also the whole, because there is no other part. So part times whole becomes x times x, and that's the same thing as x squared. So x squared equals 60, and then we would have to take the square root of both sides to solve for x. So let's see, the square root of 60 is 2 radical 15, but that is 7.7 if you round to the nearest tenth. Alright, with number 25, we're back inside the circle again. So the segments are related by part times part equals part times part again. So so looking at this chord, okay, that's these two. And looking at this chord, that's these two. So part times part equals part times part. So 2 times 3x, that's 6x, and that should equal 3 times 8, which is 24. Alright, so to solve this, we will simply divide both sides by 6. And that gives us x equals 4. And that's the answer to number 25. Now, in a situation like number 26, we've learned that if we have two tangents that converge at a single point, then these tangent segments are congruent. So, in other words, 5x minus 6 must equal 2x plus 9. So it's just a matter of solving this equation. So I would subtract 2x from both sides to get the x's together, and that's going to leave us with 3x minus 6 is equal to 9. Adding 6 to both sides gives us 3x is equal to 15, and then divide both sides by 3. So x is equal to 5. And that's your answer for number 26. Number 27, the Smith Construction Company has been hired to install a new water fountain at Winstonian Park. They would like to find the best location for the fountains so that the walking distance from each of the 3 main pieces of playground equipment is the same. How would they determine this point? Well, first of all, are they talking about the in-center or the circumcenter? Well, if we want the point that's equidistant from the vertices, which is where these toys are, so the first thing is we are talking about the circumcenter. So I'm going to write, find the circumcenter. And then we have to talk about how you find the circumcenter. Well, you find the circumcenter using perpendicular bisectors. So we can say find the circumcenter by drawing the perpendicular bisectors. Of each side. And see where they intersect. Okay, if we draw the perpendicular bisectors of each side, they should meet at the circumcenter, which will be equidistant from the vertices. Okay, so please notice that even though we are using these perpendicular bisectors to locate the circumcenter, these are not congruent. What's congruent is the distances to the vertices. These 3 pink lines are congruent. Okay, not the perpendicular bisectors. Anyway, number 28. This rectangle represents the Jones lot. The non-shaded triangular region represents their backyard. The Joneses want to build the largest possible circular pool in their backyard. How would you determine the location of the pool's center? Okay, so they want the largest possible circle that they can for a pool in their backyard. So this is the idea. But what are we talking about? If we're talking about the largest possible circle that will fit inside of this triangular yard, okay, what kind of triangle center is this? when you have a circle inside of a triangle, and we're talking about the center of that circle. Alright, this is the in-center. Okay, so determine the in-center. Okay, because the in-center is the center of a circle that's inscribed inside a triangle like this. It's the in-center, and you could find that using by finding the intersection of angle bisectors. So determine the in-center by finding the intersection of angle bisectors. Okay, so if I split this angle in half, and I split this angle in half, and I split this angle in half, okay, then they should all meet at the in-center, and that's where the center of our pool should be. Alright, that is the end of this review. I hope it was helpful. I will see you on the next video.